All right. Well, first, thanks for having me. I was uh, telling your president earlier that one of the reasons I really wanted to come here and do this meeting in person was because I had a friend actually get married at the Sperry Observatory a few years ago, and I had a really great time at that wedding. We got to see Saturn through the big telescope, which was really incredible. And I just thought the area was beautiful, so it was a really nice time, an opportunity for me to come up here with my wife and my son, who's 16 months old, so he can't really appreciate the telescope quite yet, but to really just kind of be up here for a nice little autumn weekend. So thanks for having me, and I really appreciate it. So um, that's the kind of first intro. The other thing I wanted to say before I start is that, as you noticed from my introduction, there are a lot of acronyms and words that are really specific to what I study and what I do. And I tried to calibrate this talk as much as possible to be open. But if there are things that don't make any sense at all, please feel free to stop me at any point and just catch up, because I don't want to speak above or around anyone. So yeah, thanks. All right, and then get into the actual meat of it. Did I hear a word? No, great. Um, so I'm going to talk about how the Dragonfly Mass Spectrometer, or DRAMS, will be used to explore the surface chemistry of Titan. I want to acknowledge a lot of the people who helped me directly. So the research collaborators on the screen now, and these are people who are intimately involved in this work. So it's not just me at any point in this effort. So I just don't want to take any kind of credit that doesn't belong to solely me. So it's a huge effort. And then kind of just a general outline of what I'll talk about is a general intro into Titan and why we care about it, an overview of the Dragonfly mission, and then the analysis that I and my team do in preparation for the Dragonfly mission. And first, starting with some external constraints of spaceflight and what this actually means. So I know you all are familiar with space and you work with space in a very intimate way as well. But at NASA, we do, and depending on where you work, we do really specific things. So my mission is working on in situ analysis, which is going to another planet and actually sampling things there. And that kind of work is really expensive. It's really hard to build. It's really complicated, and it takes a long time to actually make things work. So I wanted to give a quick intro into my backstory and to where I came from and how I got to the mission that I'm on now. And that actually starts with the end of my PhD. So at the end of my PhD, I was applying for my fellowship that I currently have, which is the NPP, the NASA Postdoctoral Program Fellowship. And I was actually applying to work on the ExoMars mission going to Mars, which is a joint NASA and ESA or ESA mission. And that has an instrument called MoMA, which also had this laser desorption mass spectrometer and pyrolysis gas chromatography mass spectrometry, these two different types of chemical analysis. And it was going to go to Mars, and it was this really cool mission. And it's exactly what I was doing for my PhD. And I worked with the mission team to figure out a great way to actually try to work on the mission. And I applied to get the NPP. And at one point, I had to go get a new computer because I was writing my thesis and I had burned out my charger. So I was going to a Best Buy in the Chicago suburbs. And as I'm driving to the Best Buy in Chicago suburbs, I hear on NPR that Russia invaded Ukraine. And the thing about a joint ESA NASA mission is that you rely on multiple partners. And when I heard that Russia invaded Ukraine, my heart sank, because I'm in this car driving to get my charger, and I'm learning in that moment that ExoMars is not going to be flying, because I know that Russia is actually supposed to launch the rover. So I know at that moment, I'm writing this proposal, I'm in the middle of it, and there's nothing I can do to save it. I'm, submitting it 2 days from now, and there's nothing I can do to save it. So I just go back, submit it, understand that it's going to be rejected. It was, with the caveat that great proposal, but there's no mission, so there's nothing to fund. And so I had to go lick my wounds, regroup, and then talk to the people who I was involved with. And the handy thing is that the same people that were building the organic analysis instruments for the ESA mission for ExoMars were also building the organic analysis instruments for Dragonfly. So we rewrote everything. I moved from Mars to Titan, learned an entirely new vocabulary, entirely new planetary body, and then got accepted to work on the Dragonfly mission, which has been the actual, mission of a lifetime, as I hopefully convince you of. But I just wanted to note that these missions are hard, they're complicated, they're difficult to fund, and the real push, if I can just give a sell on that, is contact your Congress people, contact your senators. Do call them because they do listen to you. I've been on the Hill advocating, and they do care about hearing from their constituents. So tell them that you care about NASA science if you do, and it does make a difference. I just want to give that little push, but also the story that space missions are also real. So now getting into the fun parts. Um, Something about Titan is it is a completely unique planetary body. So even though we don't know how life came on Earth, we can go to different planetary bodies in our solar system to figure out what the early chemistry of the solar system might have been. So what kind of chemistry might have seeded the chemistry of early Earth. And Titan is one of those extremely wild, organic, rich places that may actually give us some clues as to what organic chemistry can be, even in the absence of life. Titan is the largest of Saturn's moons. So we saw, I mean, it was a great image from the science portion of your meeting today of actually seeing Titan across Saturn. That was perfect. It was so cool, honestly. I was sitting up in my seat. It was incredible. But Titan is this pretty large moon, and it's got some pretty unique characteristics, including an atmosphere. So there's not a lot of planetary bodies in our solar system that have a true atmosphere, and Titan does. So this has been studied for a while, first in 1908, and then some methane was actually detected in 1944 as well in the Titan atmosphere. And as we'll see, that gives Titan this kind of orangey haze-like color. That's because it has this dense, thick atmosphere. And just to kind of put it into context, every other planetary body is a rocky body, and we hear this term ocean worlds a lot of times in talking about moons of the solar system. Titan is actually an ocean world. We'll get into the composition and structure of that as well. But the atmosphere is the thing that makes it really truly unique and drives this kind of like pretty wild organic chemistry on the surface. Titan is, even within our solar system, a pretty large planetary body. So it's actually a little bit larger than Mercury, larger than our moon by quite a bit. So it's a pretty big planetary body. And again, it has this pretty unique chemistry. So a couple of things that are really driving that chemistry are the surface temperature, which is around 94 Kelvin, so around negative 180 C, so extremely cold. It also has a bedrock of water ice. So it has this atmosphere. It has the atmosphere is actually 95% nitrogen and around 5% methane. It then has a bedrock of water ice, but because it's so cold, that water ice is actually about as hard as basalt. So you have this water ice, and then beneath the first bit of water ice, you actually have a liquid water ocean, and then beneath that, another shell of water ice, and then beneath that, a rocky body. So it's a pretty distinct structure. It also has a surface pressure in that atmosphere of 1.5 bars. So it is, I've heard it described as being like 60 feet down in a swimming pool. So it's a pretty heavy pressure, actually, but a light gravity, which makes it a really good candidate for a flight mission. And then something that actually was touched on earlier in your science talk as well is that the one-way light travel time to Titan is around 70 to 90 minutes, which, if you could think about that in terms of a mission operating on another planetary body, one like I'll describe, that's going to be flying around, that means we can't command it from Earth. So you can't say like, oh, we're going to hit something, don't land there. Everything has to be fully autonomous, including flight. So that's its own struggle. All right, so then again, here's this kind of like cross section of Titan. So you have the rocky interior, you have the first layer of ice on the outside, so high pressure ice. Then you have the dense water ocean, so it actually is pretty salty. Then you have another layer of ice as well here, which is again here 80 to 170 kilometers. And then the actual surface as well with the atmosphere. So a pretty unique structure, pretty compelling. And the reason that I'm involved in it, and one of the things that I think is so compelling about it, is this complex organic chemistry that happens on the Titan surface. So we have this atmosphere of 95% nitrogen, 5% methane. Even far out in the solar system, there's still enough UV light to actually start reacting that nitrogen and the methane together, which forms increasingly larger organic compounds, which then start to form an organic haze. which then clumps together even bigger to form these ever larger molecules that then fall to the surface as aerosols or fall to the surface as particulates, and then form one of the coolest features that I can describe, which is these gigantic dunes. So on Earth, we think of giant dunes of being sand. These dunes are actually fully made of, or we think they're fully made of organic compounds. So these are organic dunes of, 100 to 200-meter tall organic dunes on the surface of the planet, on top of this uh, hard ice shell. So it's a pretty wild system. And I'll get to a few more fun features about it as well. But one of the coolest is the fact that not only do we have organic dunes and we have this rocky ice, but we also have methane and ethane rain. I'm sure you've heard of the methane and ethane lakes, which kind of switch poles. We actually won't be visiting those for Titan, but they do exist. So we have this water cycle that's analogous to methane cycle that's analogous to the Earth's water cycle that's active on Titan. And just to kind of like scale the size of everything, because you see these rovers and don't often feel them in real presence, but again, dunes that are 1 to 200 meters tall, and the actual rover itself is pretty large. So when you see a picture of it, it looks kind of small, but in like when you see real sizes of it, it's about from me to you. So that's how long it is. It feels like it's car sized. It's about that big. And so imagine something that's like this large actually flying around the surface of another planetary body, and like the science it's doing is pretty wild, but the even just like outside of the science, the mission itself and flying another rotorcraft on another planetary body is pretty wild as well. But one of the things that really helps with that flight is the 1.5 times atmosphere density and the lower gravity. So apparently if you know, you could essentially flap your arms on Titan and start to fly. Here, advance through, just kind of showing some nice pictures. We're going to catch up so you feel like you didn't miss anything. We talked through all this. We'll talk through a little more as well. The structure, Cassini, nicely placed. And this is pretty much where we're at. So you missed some nice pictures, which I am sorry for. They are very pleasant, but hopefully there'll be some more as well. And then this is the spot that we were kind of like hitting on, really kind of trying to imagine yourself next to these dunes that are fairly large, also with this fairly large rover that's about to fly autonomously on the surface of Titan. Thank you for stopping me also.
How much does a dragonfly weigh?
I don't know. I believe I know it's not. I'm on science, so this one of my favorite quotes is that, or not quotes, whatever. So someone from the science team said, if scientists flew a mission to another planet, they would load a craft with all of the latest commercial instruments you could possibly get, and it would never lift off. And if engineers built a craft, they would fly a bowling ball because it never breaks, right? And so the balance between all of these things is finding exactly that. But with that, I'm on the science team, so I do not worry about weight. Okay, so then getting to a couple last bits of kind of characteristics of Titan. So Titan's years are 29.5 Earth years. The really important thing for this talk is the length of Titan's days, which are around 16 Earth days. So the way we're actually going to operate on Titan once we land is operate for a full Titan day and then sleep for a full Titan night. So we're going to be on these like 16 or 17-day cycles of collecting data and then seeing what we can do with that data and downlinking and prioritizing and figuring out what's actually going to be important, and then reanalyzing the next day. So there's going to be a lot of decision making happening in that 17 days, which is why, as earlier mentioned, I do some machine learning work as well, and that's because we're going to get really complex spectra back, and we have to be able to know quickly whether we want to stay in one location or move to a new location or take another analysis or keep moving. So those decisions have to be made relatively quickly in the science realm. So 17 days may sound like a lot, but when you're thinking through those kinds of decisions, it's pretty intense. And then some past characterizations of Titan as well. So things like Cassini-Huygens, which did a lot of analysis from around 2004 to 2017, including putting the Huygens probe on the surface of Titan. Huygens operated for around 3 hours, had a GCMS as well, which was also built by actually our general lab group at NASA as the same people, but it was from like the very early versions of that. And we actually have a cool flight spare um, in our labs of that early Huygens probe, the GCMS probe. Um, but importantly, we got some really great information back from Huygens, including that there are, in fact, these complex organic material that exists on the surface and actually exists throughout the atmosphere of Titan, but in different locations of the atmosphere. So the organic chemistry of Titan's atmosphere changes by location. We got some, of course, great mapping data from Hubble and from Earth-based telescopes, showing us that there are actual structures beneath that Titan haze. Additional flybys by Pioneer and Voyager 1 and 2. And these are showing, this plot is showing the different missions that have gone to Titan at the different seasonal cycles of Titan. Specifically highlighting here Cassini on the right-hand side of the screen, showing that it's actually in the northern winter solstice, including when Huygens landed in 2005. And that's also when Dragonfly will be going back. So we'll actually be going back at the same time of year that Huygens landed on Titan. Here showing some pictures of Cassini itself and then Huygens on the right. Again, just like kind of putting yourself for scale because it's easy to forget how large these satellites actually are. Kind of noting the desk chair in the bottom left-hand side. And so seeing these things in person, they are very impressive. And then we got some really great imaging data back from Cassini as well, showing not just the atmosphere of Titan, but also the structures beneath Titan. And ISS here is not International Space Station. It's actually the Imaging Science System on Cassini. I feel like that was poor choice of acronym, but it was not my choice to make. And then here's actually a global map of Titan. And with false colors, we can see some pretty incredible features. So the first thing I want to highlight your attention to is this kind of like darker feature in the equatorial regions. And those are actually the dune fields. So those are all the organic dune fields that have those giant dunes of organic material. We also have this pretty striking feature up in the top left-hand portion, and that's actually Kraken Mare, which is a gigantic hydrocarbon lake. So it's a methane-ethane lake, about the size of the Caspian Sea. And then we have a couple of really important features, which you'll note here, here, and here, which are impact structures. Now, impact structure, yes.
Do that again?
Yeah, so sorry. It's right in the middle is the one we're going to focus on, but there are two additional impact structures. And to note, not a lot of other additional impact structures. So we know that there is active tectonics on Titan, or at least somewhat active tectonics, or some sort of softening. What method, what form is open debate, with some people favoring other different types, but there is some form of resurfacing. So we know we don't have the oldest surface in the solar system, right? But these impacts play an additional role. And that's because, again, we have these organic dunes full of these complex organic CHN compounds, so carbon, hydrogen, nitrogen compounds, pretty wild structures. On Earth, we can make analogs of those CHN compounds, and those analogs are called tholins, which is actually a term coined by Carl Sagan, which means like muddy or unclear, and they are kind of dark. But interestingly, when you make these tholins on Earth and you mix them with liquid water, you actually get things like adenine and nucleobases and things that could be potentially prebiotic compounds that are absolutely relevant to the formation of life in the solar system. So just by mixing these completely abiotic organics with liquid water, you can absolutely form potentially prebiotic compounds. And that's one of the main questions of Titan is how far has that prebiotic chemistry gone? And what can we do to actually characterize it to better understand how organic chemistry could have progressed on early Earth pre-life? And of course, if there is life on Titan, we want to be able to detect that as well. And now I'm going to highlight some just neat pictures of features on the surface of Titan. So of course, these are flybys from Cassini doing higher resolution images to look for different surface features, including, again, these dunes. So you see these large dunes that are longitudinal. The best Earth analog to the Titan dunes are in Namibia. And there's actually part of the Dragonfly team now in Namibia doing research on the dunes to figure out how are some good flight paths, and how, if we are doing autonomous flight, which we are, how can we think about decision making along that autonomous flight path, and how to actually land in those areas in the interdune regions so that we stay upright. Again, we have these impact structures, which, when you have this impact structure close to these dune fields, it's highly likely that you mixed this complex organic carbon with liquid water, which again would then form these prebiotic compounds. How far has it progressed? Open question, but that is one of the main science questions of Dragonfly. Yeah.
What's the diameter of the larger one?
I don't know, actually. I'm sorry. I don't. That's. I'm an instrument guy, and that's that's my fault. Yes. Yeah, so the length, the scale of how long they actually craters can be stable on Titan is still an open question. I don't know how recent, and the movement of the dune fields is not extremely fast. So the wind speed of Titan, I brushed over it. Wind speed is fairly slow. It's like 4 miles an hour tops. So we don't have. It's not like you have rushing winds pushing everything really quickly across the surface. It's more of a slow progression. Time scales of how long the impact has been there, I forget. I honestly don't know. I don't want to misquote, but it's not more than tens of millions. But I don't know the exact number. And then tectonic features as well, things like faults. So again, we have an active tectonic surface. And then even potentially cryovolcanoes. So cryovolcano would be a volcano of water being the magma analog. So water spewing out of a volcano on the surface of Titan. And then getting us to this kind of like actual weather that happens. So again, we have methane and ethane rain, but that means we actually do have clouds that are going to make the methane and ethane rain. So we do have things like actually clouds that form on the surface of Titan. But again, when you have the storms, it's not a huge rushing storm. It's a much different process than we have on Earth. And then that's going to form channels. So river channels from methane and ethane. Which also leads to things like rounded cobbles. So instead of just having sharp rocks like you do on most planetary bodies, you actually have weathering. But again, because these are of the bedrock of Titan, they're actually cobbles of water ice mixed with this kind of like organic dunes. And then to put it all together, within the landing sphere of Dragonfly, so Dragonfly is going to land by the Selk impact structure in the interdune regions to first study the dune material, and then fly towards the impact structure to figure out how the chemistry changes as you get towards where the liquid water mixed with the actual organic material. And just to note again, the northern seas, these kind of mid-latitude plains areas, and then the southern polar lakes. Interesting note would be that the lakes actually, like the majority of the liquid does change from pole to pole between the seasons. But again, those seasons are on the orders of decades. So to put it all together, Titan does have the key ingredients for life. Whether or not life exists there does not actually affect our science goals, because we care about how the organic chemistry has progressed. If there is life, extremely interesting. If there isn't life, still definitely matters to know what that organic chemistry is. So our science goals are not to find life. It is to find life if it exists. But also we have the energy from the sunlight, we have the crazy organic matter, and then both liquid water potentially, as well as methane. So some questions for Dragonfly would be what makes the world habitable? What chemical processes led to the development of life? And then has life developed elsewhere in our solar system? And so we do have, of course, defined science goals to analyze prebiotic chemistry, so to analyze the chemical components and processes at work that produce biologically relevant compounds, and then to also assess the habitable environments and search for potential biosignatures if they exist. And to do that, we have our instrument suite. So DRAMS is the Dragonfly mass spectrometer that's produced at Goddard Space Flight Center, or GSFC. That's where I work. We are building it. It is very cool to see. If you want to see a picture of it on, maybe you could, actually, I can't show pictures. I wish I could. I could show pictures of other things, but I can't show any pictures of DRAMS itself, but it does exist. It is very cool. DRAMS exists in this attic space, which sits on the very top of the lander. We essentially refer to DRAMS as the heart of the Dragonfly mission because Dragonfly is centered on understanding the organic chemistry of Titan, and DRAMS is the instrument package to look at organic chemistry. We also have the Draco instrument suite. So the Draco acquisition suite, or the drill for the acquisition of complex organics. So it's essentially a vacuum that's going to pull the different samples into DRAMS to be analyzed. We have Dragons, which is a gamma neutron spectrometer. So essentially looking at bulk elemental composition. We also have, interestingly, Dragmet, which is for meteorology, because there is weather on Titan, so we've been able to study that weather. We also have a microphone, because there is going to be sound because we have the atmosphere. So you have to record it. And then Dragon Cam to get a lot of great images, which are going to be pretty fascinating. And then centering in on the Dragonfly mass spectrometer and what we actually do for analysis. So this is one of the first early acronyms was laser desorption mass spectrometry, or LDMS. LDMS is one of the types of mass spectrometry we do on the DRAMS system, so DRAMS MS. It's all about mass spectrometry. How many people are familiar with mass spectrometry? Some? Okay, great. So some, but not everyone. So I'll just give a brief intro of what kind of it means to do and what we do with it. So mass spectrometry is the idea that if you give some sort of organic or inorganic compound a charge, and you direct it into electronics, and you know when a certain mass is stable in a given electric field, and you count how many of those masses hit a certain detector at a given point and a different stability, you can essentially know what the chemical composition of that sample is. More simply, you count objects of different masses. That's the main thing. Mass spectrometry. You're just counting things of different masses. There are different ways to ionize something. So basically, you have to ionize something to be able to direct it and then to be able to detect it. So you need to give it a charge so you can kind of push it through your system. There are different ways to produce ions, and you can also do it in different ways. So you can take a big bulk sample, ionize everything, and just see what comes out. So see all the different ions that are produced. Or you can take a sample, heat it, and push things out one at a time, and then ionize those individually, so you have a more a better idea of how things are separated, and so you get a better idea of the individual components and structures of those individual components. So basically, it's counting masses, and how you treat the sample beforehand gives you a different way of counting the masses in different constraints. So there's two different ways we're going to analyze samples for DRAMS. One is LDMS, which is laser desorption mass spectrometry. That's one of my specialties. Essentially, you scoop up a sample and you shoot it with a laser and you see what comes out. Really, bonuses of LDMS is that there's no pre-preparation. So we don't need to do any kind of like fancy heating. We don't need to do any kind of fancy separation, which for a science mission that's flying on another planet is really great because that means it's less resource intensive. So we can do more LDMS analyses than we can with a different type of technique. So we can essentially scan or survey all the samples with LDMS. And if we think something's interesting, we can analyze it with the other mode. And I'm going to show these kinds of plots a lot. This is an LDMS spectra. So M over Z is just really equivalent to Dalton or atomic mass unit for these. compounds, and then each one of these is just the intensity or the count of a different ion of a different mass. So each one of these is just a different mass that we've read in whatever system that we've analyzed. And I'll explain each one as we kind of go through, but just know that this is essentially just the mass of different compounds that we see in a given sample. So if on Titan we think something is interesting, from the LDMS spectra, we can then pass that same sample in a different cup to the pyrolysis stereotypization GCMS system, which essentially takes that same sample. You can either just directly heat it up, or you can mix it with a derivatization agent, which can make select components of that sample more volatile. So as they heat up, they become volatile at lower temperatures. You can then separate those different compounds through a chromatogram or through chromatograph, through gas chromatography, through a chromatograph, and then which produces a chromatogram. And then from there, you can get individual spectra from each specific compound that comes off of that chromatographic column. So essentially, these two systems work as a team. We get different types of ions from each type of system. But importantly, again, LDMS, broad survey mode, GCMS gives us more information on chemical structures because we're separating the individual components before we analyze it. And then here's a video showing what that actually looks like. This is Draco ingesting the sample, the drill for acquisition of complex organics, ingesting the sample, which is going to go into a DRAMS cup. That's the LDMS cup. The laser is shooting the sample through a little window that we have installed. It's a gold window. Ions are then directed through into the mass spectrometer. And we can say from LDMS, all right, great, we think we have this specific fatty acid. Now, put that same sample that we ingested into a different cup, heat it up, and because we separated it, we then now not only know that we do in fact have this specific fatty acid, but we actually have chirality and intensity of the chiral compounds from that fatty acid. So we can do things like not only what's the structure of the compound, but is there an enantiomeric excess, which an enantiomeric excess is handedness of molecules, and on Earth, life favors a specific handedness. So we have a specific handedness of amino acids versus sugars. And so essentially, if you see a compound that has a specific handedness or chirality, you can say, oh, this actually came from life, as opposed to equal mixtures of both means not life, because life needs to favor one chirality or the other. Does that all make sense so far? Enough? Okay, great. All right. So then here's what I actually do. So on Dragonfly, we're going to have LDMS systems. We're going to have a pyrolysis derivatization GCMS system. I work with kind of like laboratory breadboards, or like kind of like the base models of both of those. So at NASA Goddard, I work with the LDMS breadboard, which is we named GB4, which is our Goddard breadboard 4 for this instrument. So here we actually have a laser desorption chamber where we produce ions, and then ions get directed into a mass spectrometry chamber above. So that's actually where we detect ions. Note that this kind of instrument in this configuration can't actually fly because it's too big. It's got too many different parts to stick out of it. But the thing that we can do is test all kinds of crazy compounds that we think might be on Titan, because we can contaminate this instrument and bake it back out or replace parts and do whatever we can to make sure that whenever we get to Titan, we know what we're going to see and we know how the instrument's going to react. The interesting note here is that this specific instrument is as close to the actual DRAMS mass spectrometer as you can get on Earth without being either the flight model or the engineering model. So there's a model that's going to Titan, and there's a model that's going to be on Earth that's going to be used for breadboard testing or kind of like testing of what we think we see on Titan. Those are both the flight model, the engineering model is going to stay at Goddard. Flight model, of course, is going to go to Titan. This is the closest thing that you can get to outside of those two instruments. So whatever I show you spectra-wise is as close as you can get to as actual Dragonfly mass spectrometer spectra. So pretty fun. And then this is me getting to do some work with derivatization agents in France. Funny story, derivatization agents are pretty toxic and they smell really bad, kind of like rotten fish. So you have to wear gas masks and leave the room right away. other nice note, in France, labs have windows required by law. It's wonderful. Not in the US. In the US, we're just in boxes. All right. So here's the first bit of spectra I'll show. I won't hit this too hard because I know that we're not all organic chemists, so I'll leave more time for questions, but kind of cover what I'm showing. So basically, for part of my postdoctoral work, I analyzed a bunch of different compounds that are relevant to Titan, so things that might exist, like nucleobases or fatty acids or amino acids and sugars, and things that may be indicative of life, like phospholipids or organosulfur compounds or other like true deoxyadenosine monophosphate things that are really just completely life, just to make sure we know what that spectra would look like if we got there. We produce this spectra in multiple modes. So we have positive ions that we produce as well as negative ions. And we basically have different types of spectra for different types of compounds. Then I do machine learning on all those different compounds to figure out what actually makes them separable and what do we expect to see when we go to Titan. Importantly, I also look at these like complex organic compounds, so complex CHN compounds that we think exist on Titan that make up the organic dunes. So I have actually 4 different types in my possession, but here I'll show we have 2 different types that we analyze. I don't make these compounds because there are people whose whole career are making these types of like simulated organics for other planets, but they did donate them to me, which I'm very grateful for. These are the phaser tholins, which are made at Johns Hopkins, and these are the pomp tholins, which are made at Latmos in France. So those are our collaborators in France. And just to kind of zoom in on these ones from Latmos, these are ones I got to actually be present for the making of and collect. And you can kind of see these like cool wispy structures. It was very pretty. They're also hard to handle, but it's just kind of neat to see the comparison between all of the artistic colors that we see for Titan and the drawings that we see in the actual kind of organics that we think are going to be there. So I find that fairly interesting. Beautiful. All right, and then I'm going to do a quick run through of what we think is going to happen on Titan or what we hope is going to happen on Titan. Again, thinking about these things in terms of the organics that exist on the surface and these different landing sites as they relate to the self-impact crater. So here, landing initially in the dune field in the interdune region, and then moving our way towards the impact crater. All right, so in this kind of narrative, we've made it. We're on Titan. Great job, everybody. We do our first analysis with laser desorption mass spectrometry, or LDMS. We get ions, and we see this, which if you are a mass spectrometer person, this is a mess. It's very hard to see. It's very hard to analyze or think about. So we zoom in, we see, okay, we can start to assign some ions. Let's get another sample, do another analysis. Okay, the spectra looks fairly similar. Now let's zoom in and do a high resolution mode so we can get a better view of what kind of ions actually exist or are there. We can do some sort of analysis and some sort of identification. So now we have a fingerprint of these tholins from this sample, or sure, I should say of these complex organic compounds from this location on Titan. The next step, because it's our first location, is definitely going to be pyrolysis derivatization GCMS. So first doing just straight pyrolysis. This is a chromatogram. So just to note that I'm showing these spectra for the most part, but this is actually a chromatogram. So each one of these is an individual compound or a lump of compounds that have come off of a chromatographic column. And then there's actually a spectrum for each one of these different compounds. So we can go through and actually label each one of these compounds based off of the spectrum that we get from the chromatogram. I know it's complicated if it's not your background, but essentially this is the bulk sample, and these are individual components that we can get structures for. We then do derivatization as well, so making certain compounds more volatile to get a different sample of a different fraction of what's in that sample. We can do the analysis here. So now we have our first sample characterized. We have our LDMS fingerprint. We have our structures from all of our samples. So in DRAMS terms or in Dragonfly terms, we've reached mission baseline. We have now, like, truthfully, once this happens on the surface of Titan, we've changed the way we see chemistry in the solar system. That's it. Like, we now have a better view of what actually exists. But we're going to go to location 2. In location 2, we're going to take first an LDMS spectrum again, because that's our broad survey mode. We see, similar to our first spectra, this is a mess. So you compared. So, but it's a mess with some distinctions. So this 144 peak, this methyl naphthylamine peak, is no longer present, which makes us think we probably should actually do another GCMS run because we do have some different chemistry. When we do the high mass resolution mode in LDMS still, we see that yes, in fact, the chemistry is, albeit similar, distinct enough to still do another run on the GCMS, so using the more resource intensive analysis technique. And when we do that, so here's our first Tholins on bottom with the pyrolysis GCMS runs, and our second Tholins on top with the GIST pyrolysis, and then derivatization in orange, so GIST pyrolysis in blue, derivatization in orange. And we see that there are actual chemical distinctions between these different sets. So here, we expected there to be some differences, if I can get into the weeds for a second, some differences in these chemistries because I got these different Tholins from different labs. But both labs used similar technology to produce the Tholins using the exact same gas composition and the same ratios. So that there are similarities and distinctions is pretty expected. But that we can actually map them onto the different chromatograms as well is a great thing to actually see and really important to have before we get to Titan, of course. But then you get to the actual driving question of what my research was about, which is, can you still see these Titan relevant prebiotic compounds that I showed a little bit earlier on when they're mixed with the complex organics that we think are going to be present on Titan? And this is one of those questions that like kept me up at night, like truthfully. Good news is you can. So when I mixed the Tholins with the different prebiotic compounds, so here showing adenine, the prebiotic compounds just burst out of the spectra. So to show that there actually are Tholins here, we still see this kind of like background, but the prebiotic compounds ionize much more efficiently. That could be different depending on what type of Tholins that we have, but so far everything I've analyzed on Earth, this has been the case. So we can actually see these Titan relevant prebiotic compounds even when they're mixed with these complex organics via LDMS. This is true for sugars as well as fatty acids and amino acids. So basically anything that we've analyzed in the lab, we can still see even when they're mixed with the Titan relevant prebiotic compounds. So basically for me, this was a great result. I was really happy to see it. For the mission, it's a great result. Everyone was happy to see this. So we can actually, first off, DRAMS, LDMS, and pyrolysis GCMS analysis can be used to distinguish the different types of CHN compounds. Prebiotic compounds, when mixed with these CHN compounds, can be detected via LDMS. And on Titan, both LDMS and GCMS will be useful for distinguishing these compounds. So again, chemical surveys conducted via LDMS and structures determined via pyrolysis derivatization GCMS. And then I just wanted to show the actual team of Dragonfly. So this is our annual team meeting last year. And this is not everyone. This is a fraction of the amount of people that are actually on these kinds of missions. So, I mentioned the fact that these missions go on for a very long time and they're really expensive to fund. But I just want to note also that, there are people's careers and lives who are built around these types of missions. And when you get hired on, you can spend 10 years making the valve that goes between the LDMS chamber and the ITMS chamber. And that's what you do for, 5 or 10 years. And so we all very much rely on each other. And it's kind of a unique system because if any one component fails, that fails everyone else. And we all feel that at every step of the analysis, at every step of the build. Everyone knows that you're counting on each other, and it's critical that your pieces work to make sure that the mission actually works. And outside of the money, the science and the humanity is still there in these missions. So I just want to kind of bring that point home. And that's it. That's all I got. Yes.
I would think that even though the water is locked up in rocky mountains on Titan, there would still be a significant vapor pressure of water in the atmosphere, and that it might be able to react with the solids even as they're being formed in the atmosphere. do you expect to find any oxygenating compounds away from those impact craters?
So interestingly, no, and that gets to the
What was your
temperature.
question?
Sorry. Oh, yeah. Sorry. The question was because even though most of the water on Titan on the surface is locked up as ice, do we expect there to be any water in the atmosphere? Because there may be some vapor pressure of water in the atmosphere, and could that lead to potentially oxygenated compounds from the tholins that we analyze? And interestingly, we don't think there's going to be a lot of water vapor, and that's just driven by the temperature. Because the temperature is so cold at 92 Kelvin or negative 180 C, the water is pretty much going to be non-existent. So we don't think there's going to be any kind of significant vapor pressure of water in the surface. But the idea that there never has been is the open question. And one of the things that we do specifically want to look at is degree of oxygenation to ask exactly those kinds of questions because we're seeing, with all this analysis, we're seeing a snapshot of, you see Cassini that was on the surface for 3.5 hours, or I'm sorry, Huygens that was on the surface for 3.5 hours and collected some spectra, and Cassini's mapping worked from 2004 to 2017, but like that's not the history of Titan. That's our version, our snapshot of that. So one of the things we specifically want to look at is exactly degree of oxygenation, and for that we expect there would be a higher degree of like sugars and things like that. So that's why one of the compounds that's actually analyzed is sugars specifically for that question. But for the water vapor, we think not, just because of the temperature. Yeah.
How long is the machinery going
to last? Whoa, brother. Yeah, that's open question, right? We hope baseline is one LDMS analysis, one GCMS analysis, because we have the flight component, right? So we're going to get to Titan, at the very least, do one measurement. Is that what anyone wants out of the mission? No. So we want it to last at least a year. So to go on for as long as possible, because we want to be able to sample at the dunes, go to multiple interdune locations, and then eventually make our way to Selk. So that's on the order of year, but its baseline is one operation because this technology is so new. And like I said, the ExoMars mission has a similar architecture. It was supposed to launch before Dragonfly, but now they're going to be launching at the same time from the same launch pad. So what we thought was going to be flight heritage ends up being kind of still exploration. But it's still the quality of builds that go on at NASA are pretty outstanding and pretty incredible. Watching it firsthand and seeing the people that are doing it, it has a high likelihood of going on for much longer than one analysis. But baseline is one analysis, and then beyond that, months to a few years. But we are limited by the fact that there's no sunlight, so we have to use a radionuclide generator as power source, and that will have decay over the course of the mission. And so there will be some inherent constraints on life cycle of the mission, just based on the fact that we're going to have a power source that'll die.
How do you not cross-contaminate samples?
Yeah, that's
purge the lines, so to speak, and then take your next sample.
Yeah, exactly that's a whole part of the mission, and cross contaminate samples is a really hard one, but that has a lot of heritage because our group has built the sample analysis at Mars, the SAM that's on Mars, the Curiosity mission. So that's our group as well as other missions that have gone to other planets. So we have a lot of knowledge and information on how to make sure that when we do these types of analyses, we're not contaminating the system. The harder one with Dragonfly is actually the cruise phase because we're launching in 2028. We're going to get to Titan in 2034. So that means we're going to have this aeroshell with a lander in it and all types of electronics and encapsulated foams and things that are keeping it warm on the surface. They're going to be outgassing for 7 years. So the contamination budget from the cruise phase is actually the most difficult component of contamination for Dragonfly. But with, again, like all the stuff you don't see behind the scenes of a NASA mission is a person's career, who it is to think about those questions, and not just like a meandering thought, but like calculation of every single piece of material in that system. We analyze whatever type of compounds or like parachutes or foams or whatever is going to be part of the lander. We analyze that on our systems as well. to make sure that we know that if it does get into one of the LDMS cups, we know what it looks like. But it's a huge part of the mission is calculating for contamination budget. Yeah, and it's baked into every single aspect. Yeah. Yeah.
What sort of decisions are going to be made autonomously, and what are going to be dependent on communication with Earth?
Absolutely. So things that can be done autonomously will be when to land, because we can't, because one-way communication time is 70 to 90 minutes. There's no way we can talk back, and so when to land is going to be an autonomous decision. Things like if you got enough spectra from this one sample to begin with is going to be initially an autonomous decision. When to do, so we can, I showed, highlighted one type of mass spectrometry. We can also do what's called MSMS. So essentially like breaking apart the individual components into subcomponents to then get more information about the structure. Knowing what compounds are going to be selected for that, it's going to be autonomous. But then there's going to be some, we call it ground in the loop, between the rover or the lander and Earth. Once we start downlinking data to know, do we want to stay here or not stay here? So the kind of like quick in the second, in the moment decisions are going to be autonomous, but the longer scale, like, is this enough or should we move on decisions will be done with ground in the loop. Yeah. Yeah.
Might be a little esoteric, but are you looking primarily for life as we know it, given the methane lakes, etc.? I know you're looking at prebiotics, but are people thinking about methane-based life forms?
Yeah, that's kind of the interesting thing, right? Is with mass spectrometry and the way we're doing it, it's not really biased towards, I mean, it's biased towards a carbon-based life. So it would have to be organic-based. Outside of that, like it wouldn't really matter for us because we're going to detect whatever kinds of organics are there. We're going to try to do the GCMS of whatever kind of organics are there. So whether or not, if there is a carbon-based life that isn't life as we know it, we would still try to be able to detect that. And it's, you know, we're always biased because there's no way not, there's inherently, there's no way not to be. But yeah, we detect all organic chemistry. Yeah.
So how are you going? I find it interesting that you're going to have to test this rotocraft in such a harsh environment and make sure everything spins at this terrible temperature. And you're going to have to have lubrication, and you're going to have to all these little nuances to stay, you know, viable, stay, you know. And I assume you got a department strictly on the engineering side or mechanical side saying, yeah, we're going to have to freeze this thing up to a certain point, make sure it flies.
Yeah. So there's, so the question is, how are we actually going to do this? Sorry, remind me too to repeat the question. I can forget. So the question was like, how are we actually going to do this at temperatures that are relevant to Titan, which is a pretty wild feat. And yeah, there's a whole, at the Applied Physics Lab in Laurel, Maryland, which is right by Goddard and outside of DC, at APL. And they have a whole, call it T-Titan chamber, which is this gigantic, like, I mean, it's as tall as this room, maybe like 20 feet wide, that will fit the actual lander before it goes. And it's going to go through a whole series of T-Titan testing at temperatures and pressures that are relevant to Titan to know exactly those questions, because you can't get there and hope it works, right? That's, so we have, yeah, there's a whole, but the chamber is really impressive. And like, and to be fair, all of this is done on top of all the thermal testing and modeling that's done prior, and even in individual subsystems are all going through their own T-Titan testing and their own, you know, we call it vibe, so like vibration testing and to simulate launch and everything else. But this whole like temperature is a whole additional requirement on the mission, and each subcomponent has to go through. But then the actual lander itself is going to go into the T-Titan chamber and go through analyses. So we have a whole series of analyses planned at ambient temperature and then T-Titan temperature to know what happens when we actually analyze things at that like Titan relevant conditions. And so it's no small feat, but it's going to be, it has to be completed on Earth before we go. The chamber is cool too. If you look online too, the Johns Hopkins lab has a great website where they show all these things, and they show like the rotorcraft and the thermal models and everything else, but they have a picture of the chamber, and it's really impressive. It's really cool. Yeah.
Do you have a Titan spacesuit for the mechanic to put on to go in that chamber to fix the thing?
No, no, that's like, yeah. I mean, it's truly it's a difficult thing, but no, it's yeah, no, no. But it's gonna cycle back and forth. So it's gonna go because you can't just keep it at that temperature for too long because it's too liquid nitrogen intensive. Like you're gonna run out of whatever. Even if you can keep refilling, you can't keep it going for too long. So there's a whole series of tests planned where it'll cycle from ambient, and you'll do a series of X, Y, or Z tests, and then T Titan X, Y, or Z tests, and then ambient X, Y, or Z tests. So there's a whole series planned out around how to do that effectively, so that if there is something wrong, you can fix it without it being in, yeah, a Titan suit. Yeah. Oh, let's go you, and then I'll go you, and then you. Yeah.
Were there any moving parts on the Huygens probe, and what eventually killed it?
Huygens probe was not designed to last that long. So the Huygens probe thought it was going to land in a lake designed to float because they weren't quite sure of what the surface of Titan was going to be, but it landed in a field, in like a dune field. No, it didn't last that long. It lasted, again, 3.5 hours. I don't think it was designed to last that long.
What exactly made it stop?
I think it was the lifetime of the mission. I think it was designed to not last that long, but I don't totally know. So it's a solid question, a good question, but I don't know the answer to that. Wait, that way.
Looks like it uses 4 sets of dual rotors. Is that to not have a tail section? And how high altitude is it fly?
Flying around 200 to 400 meters. And the dual rotors, the 4 sets of dual rotors, was really designed around limiting the amount of vibration, because vibration is going to be a killer for any kind of instruments. So making sure that it's as smooth as possible was the driver of the rotor configuration. And actually, the rotor configuration had to change a year ago or so because there was too much vibration induced with the old configuration. So now it's called the Vader configuration because it looks kind of like a TIE fighter, but it's cool. And then I had one over here too.
Can you elaborate more about the power source and such like kind of nuclear battery?
Yeah.
Yeah. Is it available commercially?
No. So these are actually a really hard thing to get. Yeah. What? Oh, sorry. Yeah. Sorry. So the question was, what about? We talk a little bit about the having a nuclear power source on a space mission, and are they commercially available? But like, not commercially available at all. Actually, even hard for us to get, and with current political climate, maybe even harder to get because Russia is one of the sources for things like plutonium for these kinds of nucleotide generators. But they've been flown on lots of missions before. They're very safe to operate and fly, but yeah.
Not variable.
What?
I mean, there's like 2 kinds of nuclear battery.
Yeah.
Plutonium, radioactive, not variable thing.
I'm pretty sure it's plutonium, but don't quote me on that because I'm also not designing the battery. Chemistry we can talk about. Yes.
Does your mass spec have enough resolution that you can tell the difference between, say, 2 different organic compounds, different chemical composition, but happen to have the same molecular weight? Can you tell the difference based upon isotope distributions?
That's a tough question. Yeah. So basically, the question is, does the mass spec have enough resolution to be able to distinguish between 2 different compounds that have an overlapping mass? And it depends on how overlapping they are. So our mass resolution is not bad. So if you saw the Tholen spectra, it's much less than 1 Dalton. It's not. We don't have a wide mass distribution, and we can do different tricks with. We have an ion trap mass spectrometer, so we can do different tricks with the ion trap to get better resolution in certain regions. So if we zero in certain regions, you can get somewhat better resolution. But we are also working with like state of flight, not state of the art. So it's something we kind of hit on a lot, which is we're not flying the best mass spec in the world, and we're not flying the most high resolution mass spec in the world. We're flying the best mass spec in the world that can also be the best mass spec on Titan for an extended period of time. and that's kind of like the difference is flying something that's rugged. It's the mass resolution is good, but if you gave two masses that were 0.1 Dalton apart, they probably would overlap, and it would be really hard to distinguish those two. So it's a difficult thing, and we can do MSMS, and we can try to tease things apart with structure, and you can use GCMS and use separate, because like we do have a chiral column, so we can separate things out on the GCMS as well. But it's kind of an open question of what that's going to look like, because Titan's chemistry is so unique that we're working with the best that we can fly, and whatever data we get back will be pretty phenomenal. And I personally, I work with I use the Goddard system, the breadboard for the LDMS, but I also analyze those same samples on different commercial systems that are the best commercial systems in the world in order to compare exactly those kinds of questions. So I use like TOF-SIMS and MALDI as well to do exactly that kind of thought of like what happens when we start to really increase the resolution, and what information do we gain. So it's open question and a lot of work, but it's a good question. It's something I chase actively. Yeah.
This is not a chemistry question, but are there going to be a lot of cameras on the?
Yes. Yeah.
Are they taking images a lot like they do with Perseverance?
Yeah. So that's the question was: will there be a lot of cameras on Dragonfly? And the answer is yes. So Ralph Lorenz, who is one of the Dragonfly leads and one of the primary architects of the mission, is really great at stuff like this. So not only cameras, but again, microphones and other way, like any way we can document that Titan surface environment is going to be documented, because it's going to be great images, great sounds. Yeah, it's going to make great content. Yeah.
But how is it going to land? You know, I mean, like
scary part. It's going to land. It's landing itself.
It is landing.
It's landing itself. So it's going to come out of the atmosphere. And it's going to turn on. It's going to land itself.
It's not a sky crane like they do with Mars.
No, it's turning on and landing itself. I'm not going to say anything else about it because it's too nerve-wracking, honestly, and I can't think about it. I don't want to. We're going to compartmentalize that one somewhere else. Yeah. Yeah, in the back.
How do you know which areas of like the spectrum to zoom in on?
For the LEMS spectra?
Yeah, like what's your like the clutter one? How do you know it's
That's kind of like, that's one of the things that, so the question, yeah, how do we know when to focus on what part of the spectrum or what part of the spectrum to look at? And that's one of the things that my research helps to do, is to exactly figure out that question of when we have samples that are really relevant to Titan, what part of the spectrum is most important for specific types of samples. So here I was showing the LDMS spectrum of prebiotic compounds like adenine and nucleobases, as well as the tholins. The tholins have a lot of signal in the lower mass range, so around 80 to 500 Daltons, but above that, they kind of fall off. And that's for our samples. It doesn't mean that's going to be true on Titan, but that's for our samples because there's not a lot of larger molecules in those systems, in those tholins that are made here. But things like prebiotic compounds like adenine or uracil or cytosine or nucleobases, they actually have ion clusters that extend far out into the mass range. So by comparing things like what's the different mass distribution at those different mass ranges, we actually learn more about the sample. And when we're operating on Titan, we're actually default mode is to go between the two. So it's going to be analyzing at the kind of larger mass range but lower mass resolution analysis, and then zooming in and doing a higher mass resolution, lower mass range analysis. And by comparing the two, hopefully we gain more chemical information about the system. But it's so short answer is empirically. It's empirically defined. Yeah.
Has your Mars mission that you originally were planned to be on, has that been totally scrapped? Or are they holding it on hold?
Hanging on. It's hanging on.
Go back to it.
Yeah, ExoMars mission is hanging on. It's going to still go. It's still going forward. President's budget requests, open question. We'll see how things go. As you all probably are following, who knows what's happening with funding. NASA's looking okay, potentially. Still call your senators and congresspeople and tell them that we need to be funding NASA and that we care about it. Planetary Society has a whole guide on how to talk to people about that. It's wonderful. I do recommend. But it is still planned on going. It is still planned on launching. Right now, it's pretty wild, but there's in the current schedule, there will be a time in Florida where both Dragonfly and the ExoMars mission will be in the same warehouse at the same time. Yeah, both ready for the launch pad. Yes.
Instead of calling, it's a much better idea, email. Because calling doesn't always get through. There's email that gets counted to your center.
Oh yeah, excellent. Thank you. Yeah, but calling. So the calling thing though is that they do, even if you get the aids, it still is good. Like having someone they will record. Like we've been around knocking on doors before. They will record. So email and call. But they do answer the phone and they will actually take the message. It's. I was impressed with how responsive they were, but they do respond.
When you call, you always get an aid.
Yeah, but
and I question whether how many.
they do. Honestly, we talked to the aides and like the aides pass it along. It doesn't hit a blank wall. Like the aides do pass it along and like those. I didn't know you can just go in.
So they say, but again, email.
Yeah, do both. Yeah, but the calling is effective also. It does get passed along. Especially it's a volume of calls. One person calling, not as much, but multiple people, it matters. Yeah. Yes.
The blueprint set for the machine. In other words, you're still figuring stuff out, but I've heard of a lot of science programs. Well, we'll do this, and by the time we get there, there'll be that new technology to pop in there. Can you swap out the straight 6-cylinder engine for the V8 once AI takes off?
No.
You got enough room. You're already set.
It's set. Everything is, and we're in the phase where we are in the build phase. Like right now, we're called INT, integration and testing. We are in the building things, putting it together, strapping things on. Like if there are problems, we can address those problems. Like, oh, we didn't realize this was going to affect one another. But it's more of solving the problem of two things interacting in the way you didn't expect. It's nothing's augmented now. It is going. It is.
You're in a design envelope, and there's a new alloy that led itself.
No, it doesn't matter. It's too much because those are risks, right? And for missions, those are huge risks. And so right now we are in full phase C, right? So we're in the build phase. We are past all reviews. We are Congress approved. Everyone's done. Headquarters is done. We are building the mission as it is, as it stands, and that is what's going to be flying to Titan. Its designs are done. Yeah.
I remember a phase at the moon landing experiments many years ago. They were not really sure how soft the regolith was, that it might just land and sink out of sight. Do you know how strong those Tholen dunes are?
We can't land on the dunes. That's why, yeah. How strong are the dunes, and are we just going to sink into the surface of Titan? Very good question, and something we all are scared about. But we can't land on the dunes themselves because they would probably be fairly soft. But we can land in the interdune regions because those should be bedrock of water ice. So we're planning to land in the areas that are more sturdy with less open questions.
I hope it's smart.
Same. Yes, I also hope it's smart. Yes.
So the pod opens up, this thing drops out, it starts up, it starts flying itself. It's looking at the ground where it's deciding to land. And it goes, whoa, can't land there. Whoa, can't land there. How long can it stay aloft at any given time?
It's not short. I mean, the flights are planned for 20, 30, 40 minutes. Like it's not short. It's not hard to fly on Titan. That's kind of the bonus is you can fly for quite a while. So I don't think that's as big of a problem. Yeah. So yeah. All right.
Thank you very much.
Yeah, my pleasure.